This yesterday we talked about this full ladder using two half adders.
Yeah.
Today we talk about MUX.
Yeah.
It's multi. So this has like this, like we have two inputs A, B, and
Yeah.
one output and one select line.
Yeah.
So this one and this is 2 by 1. Uh, so there is a concept, there is a formula, mathematical formula, like on what basis we select this select lines, how many select lines are required. So
Okay. Yeah.
because, for example, if you're talking about like four inputs, A, B, C, D.
Yeah.
In this case, we say that here, yes, and the number of select lines are 2. So
Yeah.
what if we do not have four inputs? A, B, C only we have. Then how many
Yeah.
select lines are required? So like that. So for that, um, this is like a 2 power of select line must be greater than or equal to number of input line.
Yeah.
So now, for example, if I am having, let's say, number of input lines are 3 in this.
Yeah.
In
Yeah.
that case, if I'm thinking like I require only one select line, then this is not satisfied, this equation.
Yeah.
So
Yeah.
I have to go for instead of 1, then I have to go for 2.
True.
That way, we come to a conclusion that how many select lines are required
Right.
based on
Uh,
this one.
the input. Yeah. Equation and the inputs,
Uh,
basically.
so based on
Uh, in Mux, is it necessary to have enable always?
we do not have enable, no? This is select line.
Yeah. But apart from select line, enable is necessary to have, or is it not necessary?
Enable is not required. Why enable is required here?
Okay. No, like usually in the like making a 4:1 mux using 2:mux, we sometimes use enable, right?
No, no, we don't use. I will talk about that.
Okay. Okay. Okay.
So this one is again this two input here, and this is
Yeah.
one select line and one output here Y, and the
Yeah.
other one is we have four inputs A, B, C, D, and this is 4 by 1 and this is 2 by 1. So
Yeah.
based on that, we now can tell that two are required
Right.
lines. So even if you have A, B, C, then also the select lines required are 2.
Two. Okay.
So
So if we have three
now,
inputs,
uh,
one
huh,
one question. If we have three inputs and the fourth input is not used, the D,
hmm,
and we still have two selects line,
hmm.
and what happens to the fourth input, the D?
We'll
Like
talk
we
about
just
that. We'll talk about that.
okay.
So now this is 1, 2, 3. And that always that formula we have to have in mind, like 2 power number of
Yeah.
select lines greater than or equal to number of input lines.
Yeah.
So this we have to have in our mind. Now, let us put this functionality in the table form.
Yeah.
So, when S is 0 on the output, we see the A. When S is 1, on the output, we see the B contents. This is a port. This A is a port. B is
Yeah.
also a port. Y is also a port. This S is
Okay.
a control port. This is also a port. So this port may have a port. The name of the port is A. This port may have 0 or 1. This port also may have 0 or 1.
Yeah.
So
Yeah.
depending upon your select line value, you may get the port contents. A means A port contents. A port can have 0 or it can
Yeah.
1.
Okay.
So now coming to four, when we have the four input lines, then we say that here 0, 1, 2, 3. Because this S is a vector here. So
Yeah.
that's why we are just putting a S here. If you take the scalar, then you can put like S1, S0 like that.
Okay.
So in that case, it is like 0, 0, this is 0, 1, this is 1, 0, this is 1, 1.
Okay.
So even this S is vector means the size of this vector is 2-bit.
Yeah. Right.
So this 2-bit means this S is now, since it is a vector, S of 1, S of 0, like that it is.
Yeah. Yeah.
So, this understanding we must have.
Okay.
Now your output is here A, B, C, D.
Hmm.
So this is okay for 4 input. Now
Yeah.
this we have to think like how it should work when we have, let's say, A, when we have B, and when we have C, but we do not have here a D. The fourth one is not there.
Yeah.
Then we have to think like a physical device, how it should behave. That we have to think.
Yeah.
So
Okay.
physical device, you have, let's say, S1 and S0. So for 0, 0, okay, that is fine. You are giving here A. For
Yeah.
0, 1, you are giving B. For 1,
Yeah.
0, you are giving C. That's fine.
Yeah.
But when you come to the 1, 1, then this Y is a physical device. It is a physical device. So
Right.
physical device will have this is 0, 0. So this is 0, 1. This is 1, 0.
Yeah.
So
Yeah.
physical device cannot have here, um, like there is no value kind of thing will not be there here.
Yeah.
So either it should have 0 or 1 available.
Yeah. Yeah.
There is something called high impedance state.
Yeah.
High impedance state. This high impedance state, we have to understand is physically like what is high impedance state. So, for example, we have this inverter, and we are giving 1 here. So when this is enable, this is the control signal.
Yeah.
So enable is there. As long as the enable is there, when you give 0, then you get 1. When you give
Yeah.
1, you get a 0.
Okay.
What if we are removing the enable?
Mm-hmm.
So now this is in terms of the physics,
Transistor.
the transistor level. If you think here, we have VDD connected here,
Yeah.
ground connected here. We are giving input here, and we are getting the output here.
Yeah.
Then there must be this enable also na, in this figure.
Yeah. Yeah.
So where to keep that enabled? So this design is not having enable.
Yeah.
This design not having enable. Now where to keep that enable is the question. So
Okay.
question to answer that. We have to think about that. You have this device. Enable, when enable is there, one, then what is
Yeah.
uh, enable? Let us just put here somewhere later we will connect.
Yeah.
Enable is one here. Enable is one means now whatever you give it, it is working. If you give one, then this one is supposed to be going here.
Yeah.
And if we give zero, this zero supposed to be going here. Then how is that we make it possible?
Yeah.
Somewhere this design may require if you take AND gate, then if you think like you are giving here one
Yeah.
uh, enable one. So if it is zero, then it is zero. If
Right.
if it is one, then it is one.
Yeah.
So extra circuitry is required. What I mean is
Yeah.
this alone cannot handle the enable.
Right. Right.
You require to have extra circuitry through which
Yeah.
you are passing this value,
Right. To
this
make it
output value.
work. Yeah.
This device is actually controlling.
Yeah. Right.
So now, let's say when this enable is not there, then high impedance state means what? Then physically, let us think in a physical quantity. Like if you are measuring, you are using an ammeter, you are
Yeah.
using a voltmeter, then
Yeah.
in the circuit there may be current, let us say we put here resistor and we measure here current like this,
Yeah.
and we measure here voltage like this.
Right.
So now a high impedance state, how can you model? How can you tell? How can you physically imitate it?
Okay. Yeah.
I'm asking.
I don't remember.
No, high impedance state. What happens in the high impedance state? There will not be any flow of current. First of all,
Yeah. Yeah.
this resistor is a high impedance. We are saying
Yeah.
impedance is generally we have this XL, XC, and R.
Yeah.
So R is the resistance, capacitance, inductance.
Right. Right.
These two will have something called reactance
Yeah.
plus resistance.
Yeah.
These together will give us the impedance.
Right.
So now how we imitate that? Because let's say you are keeping this, imagine, just imagine, this is a high resistive material.
Yeah.
In that case, we can keep open like high resistive means we can model
Yeah.
this
Open. Yeah. Open circuit.
open.
Yeah.
If it is open, now what happens here? This voltage will not find a path. This is not the
Yeah.
closed circuit.
Right.
So when this is not the closed circuit, though you have put the voltage, trying to measure the voltage,
Yeah.
you will not have any voltage drop across this
Yeah. Yeah.
because this is open.
Yeah. Open circuit. Yeah.
And even the ammeter will not show any current here.
Right. Yeah.
This is open here,
Right.
this part.
Yeah.
So this kind of behavior is no, we don't see the voltage drop, we don't see the any
Yeah.
current.
Yeah. No current. No
So
voltage drop.
something like that.
We want to.
In this MUX,
Okay.
what is that we can do like here 4 by 1 when this condition arises 1 1.
Oh,
So whether we have to imitate the behavior of high impedance, then high impedance means
okay.
what again? Again we have to answer what it is.
Yeah.
Is it
Oh.
zero is a known logic value,
Right.
one is a logic value, known logic
Yeah.
value. We have
Yeah.
something called X, we have defined unknown,
Okay.
and we have defined something as Z that is for high impedance.
Okay.
So
Okay.
now what is that we can do is this when one case comes,
Yeah.
either we have to model the device for high impedance.
Okay.
At the output, you will not see like any value, known value to you, neither zero nor one.
Yeah.
It is not having any meaningful value to you.
Okay. Okay.
So
Got it. But
meaningful, that is one case.
okay.
The second case may be you don't care having a zero or one.
Okay. Yeah. Then
So that is the second case. In
okay.
physics, what I am
Yeah.
trying to tell you is, I am trying to tell that A, B, C, these are known to you.
Yeah.
You have S1, S0. For A, you have known value 0 or 1. For B also you have known value 0 or 1. For C also you have known value 0 or 1.
Yeah.
But when your select line gets 1 1, then
Yeah.
this on the Y, we have to either design like it is behaving like a high impedance, holding a high impedance, or
Yeah.
don't care having a 0 or 1.
Okay. Yeah.
So only these two are the physically possible. Like any device,
Yeah.
if you are manufacturing
Yeah.
physically, only these two are the possible cases.
Okay. Yeah.
So that is one case that we can try to understand. We can
Yeah.
try this way to understand this one. The
Okay.
other way is last value, whatever it has given, that it has to hold. Like
Okay.
what I mean is 0 0 0 1 1 0. In among this,
Yeah.
whatever maybe the last condition arises, it may be 0 0, or it might be 0 0 1, or it might be 1 0. But
Yeah.
among this, any one may be the last that had occurred here. Later on, if this is
Yeah.
happening, whatever had occurred last prior to this, that
Okay.
value it has to hold.
Oh, how is that useful?
No, no. Yeah, no, no. Okay, I will answer that. But this is
Yeah.
another possibility I'm telling.
Okay.
We are not talking now about the usefulness. We are trying to understand what might be the possible cases.
Okay.
This is one possible case. This one, case one, this one.
Yeah.
Case two
Okay.
is case two is we may have in our mind that
Yeah.
whatever might have occurred last prior to occurring the 1 1,
Yeah.
this circuit should retain the last occurred value
Yeah.
on the output.
Yeah. Okay.
That might be the another case that we may be thinking.
Yeah.
The usefulness of that we are not thinking now. We are thinking how to answer this 1 1 case.
Okay. Yeah.
Our primary
Oh,
concern now is how to answer this 1 1 case.
yeah. To how to retain the previous value.
So, but in this case, what happens is it will not be a combinational circuit then, because
Yeah. Then.
moment when we talk about retaining something,
Yeah.
then it is either latch or a flip flop,
Yeah. Yeah.
because latch and flip flop only have the property of retaining.
Yeah. Right.
So that's why we don't try to model this way any combinational circuit. We don't associate latch or flip flop with that.
Yeah. Yeah.
So in that case, it then the valid answer could be modeling like this only, high impedance state or this
Yeah.
we don't care
Zero.
like having a
We
zero.
don't care. Yeah.
So
Yeah.
that is what the only possibility.
Right.
So when our MUX, primarily why we use this MUX is another thing that you asked, like applications of this.
Yeah.
So when we want to have a local you have the chip.
Right.
This is your chip. On chip, let us say here is one IC. This is SoC chip. SoC is having multiple ICs
Yeah.
on the same silicon wafer.
Okay.
So here is one IC. So now some this IC1 wants to communicate with this IC2,
Yeah.
but for establishing the communication between these two devices, let's say we require to run here several wires here.
Right.
So our challenge is to minimize the wires on chip.
Okay. Yeah.
So there where this will find the application.
Okay. Yeah.
So what we do is instead of running so many wires like that, we keep
Yeah.
one IC1, we keep one MUX IC here,
Okay.
and we keep another DMUX IC.
Now.
So then we have the IC2.
Okay.
So
Okay.
we give anything to this MUX,
Right.
and then we run only single
Mm-hmm.
wire,
Wire. Wire.
and we keep the select lines here required,
Okay.
and then we transmit this here to this IC.
Okay.
So now we are having the burden of having the wires here, burden of having the wires here, but we are able to minimize the wires required here.
Right.
So this
Okay.
is the on like like uh th this is internally to this chip, but we are not running uh, what we say routing area. This is
Okay.
the routing between the ICs.
Okay. Yeah.
On chip again, we require to run anyway this one.
Yeah.
So somewhere this helps like minimizing the number of wires. That is
Right.
one application.
Okay.
So like that, the other application you may Google, you may find where it is
Yeah.
used.
Yeah.
So primarily, that's how we are using this MUX, and mostly we don't use this way on chip like this. There is something no on chip also we use, but there is another thing apart from that on chip. We say it memory.
Okay.
Several memory ICs are there. This is IC1, IC2, IC3. Several
Mm-hmm.
ICs are there. So memory, one is memory, and the other is registers, on-chip registers.
Okay.
And on-chip arithmetic logic unit, ALU. So
Mm.
now you have some this memory, inside this memory some contents are there, them you have to bring here to the registers, and
Mm-hmm.
registers will give those contents to the ALU will perform and it may wants to write back to the registers again. You
Yeah.
may wants to again write back to the memory, if memory required, then you may wants to write back to the memory also.
Okay.
So now what is happening here? Here, uh, few wires are required here.
Yeah.
Here wires are required. Here wires are required. Here wires
Right.
are required. And apart from these wires, you also will have several flags,
Okay.
zero flag, and overflow flag,
Okay.
sign flag.
Yeah.
So from ALU, few wires may be running to all of this also, overflow, sign.
Right. Yeah.
And one, two, three, four, and here five.
Yeah.
So all over wires are running here.
Okay. Yeah.
So which is
Everywhere.
impractical if you put all of this, you wanted to put on a silicon.
Yeah.
So it is impractical to handle several such wires because the area here we may be having maybe 45 by maybe 55. This may be again at micrometer or nanometer.
Yeah. Yeah. Yeah.
So at that level, we uh, we cannot afford running all over wires like this.
Yeah.
So then people
Okay.
thought, bhai, don't keep like that. You keep, there is a bus concept.
Yeah. Is in the bus concept the protocol comes in?
Yes, yes.
Okay.
So there is a bus concept. Now everything will communicate to the bus.
Okay.
Memory will communicate to the bus. Your register set will communicate to the bus. Your ALU will communicate to the bus. Your
Okay.
flags will communicate to the bus like that.
Okay.
So now, but communicating is done through the MUX.
Right.
So there where MUX will find the application.
Okay.
So
Okay.
now let's say,
Which one to select? Like out of memory register and ALU, which one to select? Then we use marks.
ah, ah. So,
Okay.
this is common bus, CB, common bus.
Yeah.
So any data memory, let's say memory wants to keep something to the register. What it does,
Yeah.
it requires to first access the bus.
Right.
So how it will access the bus? Let us say we have given 0, 1, 2, like that.
Yeah.
So when select line is 0, 0, then memory is accessing the bus.
Yeah. Yeah.
Then memory will keep its contents depending upon the additional controls, read, write.
Okay.
There are lot many things like that.
Right.
So what we want is memory. We want memory to keep its contents onto the bus. Means at that time, along with the MUX select lines, we also have to enable the read signal also.
Right. Right.
So then
Okay.
only we can read that location.
So okay. So
So
first we
listen,
put
listen. Let me complete. So now let's say to put these contents onto the
bus.
bus, let's say 5 nanoseconds are required.
Okay.
After 5 nanoseconds only, in the instruction, let's say we have something, whatever the memory has kept, that should come to the ALU, let us say.
Okay.
So at that time, what happens is after 5 nanoseconds, the select lines will be now enabled as a 2.
Okay.
And ALU has got several inside again. Yeah, arithmetic
Yeah.
unit are there, logic units are there.
Yeah.
So it also has got some controls.
Right.
So depending upon that, now the bus is occupied with the memory contents,
Yeah.
MC.
Right.
And this memory contents can go to the ALU, can go to the registers, can go to other units also.
Yeah. Yeah. Yeah.
So that is managed through the control signals that are there with every module like this.
Okay.
So
Okay.
there where this muxes will play the role of a role to control the common bus.
Okay.
So this common
Okay.
bus helps us to minimize this number of wires are running all over, na?
Yes. Yes.
So it will help us to minimize these wires running all over.
Okay. Yeah.
So
So
the
it's also helping us in selecting memory register and ALU,
many
and
things.
also
This is vague idea I gave. There are several other
yeah.
things.
Right.
But our main focus is on like to understand the usage of
Marks.
MUX.
Yeah.
So that's how
Okay.
MUXes are used inside the IC.
Yeah. And the example that you have given, this happens in a chip or in a SoC?
This happens in everywhere. Like a single chip also it happens in SoC also
Okay.
it happens. SoC is more like there will be more like to handle MUXes
More chip.
usage will be more in SoC.
Okay. Okay. Got it. And in
Uh-huh.
above that, you in the inverter, like the transistor inverter that you showed, how are we able to uh, operate using the don't care and the high impedance there? Like if we want to physically draw or make a
Now,
circuit, how is that happening?
Physically, there are two possibilities, like maybe high impedance or we don't care, like zero or one.
Yes.
These are
Yeah.
the
But
physical limits.
how, right? This we can implement in the code or in Verilog by writing, but how is it happening in the transistor level? That I want to understand.
Yeah, very log level, what you do is you define that coding part hasn't come yet.
Okay.
But since you asked, I'm just telling. So what you do is,
Yeah.
uh, what we do is always at the rate. Let's say you are keeping you are defining here. Let's say begin k,
Yeah.
yes, then 0, 1, 2. So y you assign A, y you assign B, y you assign C.
Yeah.
Now, you either have to put the default statement here.
Okay.
Default, what is your y is,
Yeah.
because s is two bit. 2 bit means
Yes.
we have 0 0 condition, 0 1 condition, 1 0 condition, 1 1 condition.
Yeah.
For 0 0 you have addressed here. This is 0 0.
Yeah.
For 0 1 you have addressed. For 1 0 you have addressed.
Yeah.
But for 1 1 it will produce the latch. We don't want latch. We
Yeah.
want it to produce something known value
Don't
for
care.
you.
Yeah.
Don't care.
Yeah.
So
Don't care or high.
you put that you handle either putting the default here.
Okay.
You put default and you put what your y is supposed to be. Like
Okay.
if you are keeping x here, that is one tick bx, then
Yes.
this is unknown.
Okay.
And if you are keeping one tick BZ, then that is high impedance.
High impedance. Okay.
So
Okay. It's like,
otherwise what you do is, even before getting into this case statement,
yeah.
without a default this entire thing, you
Yeah.
put here statement. What is your
Okay.
Y default is?
Okay.
Is it unknown value means you don't care that,
Okay.
or is it high impedance?
Okay.
So
Okay.
then what it does is it will not going to produce for you when you synthesize, then it is not going to produce any latch there.
Yeah. Yeah.
So it will produce a combinational circuit only, which can handle these cases.
Right.
So that's how you
Okay.
handle in Verilog.
Okay.
Okay,
Yeah.
okay, let us continue with our discussion then.
Yeah.
So then, so like that, this formula anyway you keep in mind.
Yeah.
Then let us come to the coding part of that. So in the coding combinational, when we do yesterday, I told switch level is not supported by the synthesizer.
Yeah. Yeah.
You either have to go with the gate level
Yes.
or data flow or
Yeah.
your
Structure,
behavioral.
behavior. Yeah.
So now what happens is, in gate level, the problem, as I told, you have to have that understanding like what gates are required for you. Like
Yeah.
for example, like if you are going with this S1, S0, 0, 0, 0, 1, 1, 0, 1, 1. Then you have here your Y. Then you have your A, B, C, D. Now from here we have to get the Boolean expression like Y equal to A S1 bar S0 bar plus B, this B, and then this S1 bar, and this S0, this S01. Then
Yeah.
plus C, then this S1, this S1, and this 0 means S0 bar,
Yeah.
plus this D itself, and then this S1 and S0. Like that, we have to first have the Boolean expression.
Right. Yeah.
After that Boolean expression, from here we come to know that we require to have the S1 bar here. We require to have the S0 bar. So it means what? Two two NOT gates are required.
Yeah. Yeah.
Then I can produce S1 bar and S0 bar.
Yeah.
Then to produce this entire thing, I require one three input this AND gate.
And gate.
Like
And
that, we require to have this
yeah,
knowledge.
yeah, yeah.
So, but as I told, in industry, this helps if designs are very smaller, because our main aim is either you go for the FPGA or
Or the asset.
uh, ASIC design.
Yeah,
So what happens is, for smaller designs at the gate level, if you could able to code your design, then what it does is this FPGA compiler here,
yeah,
this compiler will map to the lookup tables here.
yeah.
But here it is going to map to the, this is map to the standard cells,
Okay. Library.
standard cell library. In a standard cell
Yeah,
library, let us say, there is a foundry ABC1, ABC2, ABC3, like that, three foundries we have. This foundry not having, let's say, any MUX standard cell. This ABC1 is not having, okay? Are you there? Mm, your voice is not coming. So, uh, till uh,
Foundry you mentioned.
which point you were?
Foundry. You said there are AB1, ABC1, ABC2, ABC3 foundry.
Huh. So let's say ABC1 foundry is not having MUX standard cells, okay?
Yeah.
But ABC2 has got only MUX 2 by 1, okay?
Okay.
And ABC3 has got MUX 4 by 1 MUX, starting from MUX 4 by 1.
Okay. Okay.
So now what happens is, when you try to map for that Verilog code, that code that you wants to map through the compiler, ASIC compiler,
Yeah.
this compiler, if using ABC1 standard cell library, which is not having MUX, then it has to implement using available gates.
Okay.
That's how it
Okay.
works.
Okay.
Now,
And this
uh
standard cells are made by using those compact model thing, right?
no, no, they are not. That compact models are that those are for different purpose. Compact models are those are analog side behavior. Standard cells are different. For just a minute. Standard
Because
cells, for example, you this is XYZ foundry. Their job is to develop this standard cells.
yeah,
So what they have done is, they decided to have uh, maximum four input AND gates.
right.
Two, three, four. And they decided to have this four input NAND gate also, and they also
Yeah.
decided to have four input this NOR gate,
Okay. Yeah.
and they decided to have D flip flop.
Right.
So what they do is, let's say, they in their lab, they are working at let's say 22 nanometer.
Yeah.
So at 22 nanometer, for different input, four inputs, AND gate means 2 power 4.
Yeah.
2 power 4 means
Yeah.
total 16 possible cases will rise.
Right.
For all those 16 possible cases, what is the power that it is consuming? what is the
Uh,
area that it is consuming, what is the delay it is going to produce, all that they evaluate.
okay. Everything.
Similarly, for every gate they do this work.
Okay.
Having done that, they develop some format acceptable to the compiler.
Okay.
This is like a text
Yeah.
file.
Yeah.
So this text file, they put they have this syntax of
Yeah.
acceptable to the compiler.
Okay.
Now they put here, let's say they are putting a gate equal to, this is the syntax, let us say, and
Yeah.
for for case 0 to case 15, like because it is total 16. No?
Yeah.
So at case
Yeah.
0 again they put what is the power it is consuming, what is the area it is consuming, what is the delay.
Yeah.
So like that they put a big file like this.
Okay.
Now this is what is a your library.
Yeah. Standard cell library.
Huh. So apart from that, they also put what is the parasitic that capacitance that may
Yeah.
come, capacitance effect.
Yeah.
What
Yeah.
is the resistance?
Perfect. Yeah.
All
All.
that all that they put here in this file.
Okay. Yeah.
So now
Uh,
now what they do is this file along with the Verilog file, if you are giving to the compile ASIC compiler.
yeah.
This SC compiler is so cleverly designed that it reads this file and it reads your Verilog code and it
Yeah.
maps what gates are required to build the Verilog code.
Yeah.
Got it?
Okay. Yeah, but one question. I
Mm.
have used standard cell library in Virtuoso also, which is meant for mostly analog design. So that's
That's what I'm saying. Nah, that is this is I'm talking about the digital design.
yeah.
In an analog design, you don't have standard cells. What you have is uh, you have there all transistor information there.
Yes,
Wait,
but in
hold on. I'm coming to the analog part.
okay.
In analog, you don't have any standard cells. In analog, you this particular transistor at 22 nanometer, how it behaves, all that information.
Yes.
If foundry is supporting fabrication of capacitance, then that information.
Yes.
If foundry is also supporting some level of resistance fabrication, then that information.
Yes.
If foundry is supporting inductor of that information.
Right.
So all this, they have the some file called that they call it as spice models are there.
Yeah.
Spice models. Of that spice model, they also have like a first of all, we in analog approach, how it is? It is this way. You do first a schematic.
Yeah.
So
Yeah.
when you do the schematic, if you want to verify your simulation results, the way we take the standard cells in digital, we take here spice models
Yes.
and
Okay.
your netlist file, that is a schematic.
Okay. Yeah.
They go to the analog compiler
Okay.
and it exhibits results
Okay.
depending upon the delay, parasitic, that information in the 22 nanometer, how this transistor is behaving, and if you
Yeah.
have used in the design any capacitance, any resistance, any inductor, all that netlist will get information from this spice file.
Okay.
And it will accordingly produce the results here.
Okay.
But you want, let us say, okay, forget about what you want. It produces the results. Now, what you want is You want to generate, you are satisfied with these results. Now, this netlist, that is schematic, you want to send to the foundry.
Okay.
So this foundry, when you want to send, you cannot send, this netlist is not acceptable for them.
Yes.
This is a schematic netlist.
Yeah, yeah.
They want layout netlist.
Yes.
So at the layout, you require more information at the physical level. This is physical level.
Yeah, yeah.
So at the physical level, you even include here. You might not have this spice model might not have some parasitic effect.
Okay.
So this physical design, when you make these models, these files will have that information.
Okay. Okay.
So what is the meaning of that? Means let's say you are designing like this. You have kept the poly like this poly.
Yeah.
This is your poly, and this is your diffusion.
Okay.
So for foundry acceptable, let us say here 1 nanometer for foundry.
Yeah.
For some reason, you have kept it 2 nanometer.
Okay.
For some reason.
Mm-hmm.
Now it evaluates like what is the parasitic capacitance that is produced because of this extension here, that for some reason in your design you extended this poly here.
Yeah.
So that information it fetches from this parasitic information at the foundry level in the lab. What they have performed, I told na, they keep the text file.
Yes. Yes.
From that text file, that compiler is so cleverly designed that it reads this text file given by the foundry at the physical level information,
Yes.
and it takes the geometry, that is layout, geometry, that is
Okay.
layout,
Yeah.
it produces
Yes.
the results.
Okay.
So you run this simulation is called post layout simulation.
Yeah. Yeah.
This simulation is not post layout simulation. This is not
Yeah.
post layout.
Okay.
This
Yeah.
is the post layout.
Okay.
So now post
Yeah.
layout simulation results, you are happy.
Yes.
Now what you do is you generate a file called GDS here.
Yes.
So this file is what required by the foundry.
Okay.
So from here, very clear that in analog design, we do not have any standard cells.
Okay. Yes.
We have to have the schematic design. If so, here what people do is they don't go for the schematic. Instead of going to the schematic, they develop the compact models.
Yeah.
So this is written in a Verilog A
Yes. Yeah. Right.
or Verilog AMS. So there we can design any schematic component.
Okay. Yeah.
And even these models will run with the help of some other file also, because only
Yeah.
models cannot do anything, because these models require to be provided with some foundry information.
Yeah. Yeah. Yeah.
So you either go with a compact model design or you go with a schematic design. You do not have any standard cells here. You have only spice models.
Okay. Yeah.
And
Yeah.
then layout is there. In the layout, you do not have any standard cells here. You can automate layout to some extent only. And then here also you have some foundry given files. Then you have to use,
Yeah.
that is called post layout simulation.
Okay.
Whereas,
Yeah.
whereas in digital IC design, we
Yeah.
we don't do any schematic job.
Okay.
Schematic
Yeah.
job,
Yeah. True.
schematic job is done by this standard cells.
Yeah.
Standard cell information is this compiler is different. This compiler, what it does, it reads ABC1 or ABC2 or ABC3 standard cell library, and that compiler is so cleverly designed that this Verilog code, what hardware it maps to, and then
Yeah.
it picks the components from the foundry given file.
Yeah. Yeah.
So
Yeah.
hope your question been answered.
Yeah. 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 This was always a one doubt, like what
Hmm.
is the difference in the
Hmm.
digital and analog? Yeah. Yeah.
Hmm.
Thanks for the
Yeah.
explanation.
So now, uh, here the problem with this gate level modeling is this,
Right.
that you have to have the knowledge of this Boolean expression.
Yeah.
But this is not done in industry. In industry, very rarely this is used, but it helps in converting from Verilog to the mapping this Verilog code
Yeah.
to the standard cells.
Yeah.
It is a job of this compiler.
Yes.
Because you only telling that you require this gate.
Yeah.
You
Yeah.
only telling that you require this inverter. You only telling that all that gates information. You only telling, na.
Yes. Yes.
So compiler is now free to map, na.
Yeah.
So it job is only to pick the components from the standard cell library and just produce the foundry specific netlist.
Right. Yeah.
So that way gate level modeling helps.
Right. Yeah.
But the when you go for the data flow or behavioral level modeling, then
Yeah.
let's say if you model at gate level,
Yeah.
it is taking 5 minutes.
Yeah.
If you do with the data flow or behavioral level modeling, it may take 20 minutes.
Yeah. Yeah.
Why? Because it has to first of all try to map from the Verilog these expressions to the
Yes.
generic logic.
Yeah.
From generic logic, it has to read from that foundry given file and produce a foundry specific netlist.
Right. Right.
That's why it takes more time when you model it data flow or behavior level modeling.
Yeah.
For bigger designs, this difference is seen.
Yes.
Okay,
Yeah.
so that's why this coding, let us avoid doing this one because you can practice later.
Yes. Yeah.
Let's do with the data flow because data flow is we use
Yeah.
in industry. Now,
Yeah.
when you use the data flow, again
Mm-hmm.
here, let's take this smaller example. E, B, Y, your select line. So now here, when you do with the data flow, there are various ways here to do.
Okay.
The best way is best usage of available operators.
Right.
So this comes through the lot of practice. So several designs, if you do,
Yeah.
try. You can understand like which operator I have to pick.
Okay.
So, for example, from here, what we can understand is when S is 0, I require A. When S is 1, B will come on to the output.
Yeah.
So here it is A S bar plus B S. So I can produce this one using the assign keyword. And
Mm-hmm.
then this one you can assume as the Y1 and this you can assume as the Y2.
Yeah.
Y1 is A and this is ampersand and here negation of S semicolon.
Okay. Yeah.
Now one more assign and then Y2 and then this is B ampersand S. Now
Okay.
another assign, another assign. Now Y equal to Y1, this bar, this is pipe symbol,
Yeah.
then Y2. So this is
Okay.
one way of coding. The
Okay.
other way is there is a conditional operator in the data
Right.
modeling. So how we use that means directly like this. When S is question mark, we assign B, else A. So this is
Yeah.
conditional operator or ternary operator also. So here
Yes.
the meaning of keeping S means is S equal to 1? That's what you are actually meaning there.
Yeah. Yeah.
So in that case, if it is true, then this first statement is executed. That is called we for understanding purpose. We say it's the statement, true statement. Uh,
Yeah. 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 True.
after colon, this is like a else.
Yeah.
And then this is false statement.
Okay.
If this
Okay.
condition happens
Yeah.
to be false, then this false statement will be assigned to the y.
Yeah.
If this condition, this yes is true, then this true statement will be assigned to the y.
Okay. Yeah. Got it.
So now this is also data flow modeling. This is also data flow.
Okay.
But the
This
clever
is,
usage of this operator will ease our job.
yeah. Yeah. But inside, once we do that, the synthesizer and all of those thing will operate similarly in both the cases.
In, in this case, you mean how compiler works?
Yeah, I mean, what like once we are doing, for example, if we are putting this code, and you mentioned the synthesizer for for example FPGA, if
Hmm.
we are using this and the synthesizer works similarly in both the cases or
90,
differently because
90, 99% they work in a similar
oh, okay, okay.
because the
Can you give me 2 minutes? I will just come in 2 minutes.
uh, okay.
Yeah, just 2 minutes.
Huh. So 99 percentage they behave similarly
Okay, okay.
because those algorithms are sophisticated algorithms. They
Yeah,
try to map, to the optimized netlist.
okay.
So either this way or this way, they kind of like
Yeah,
they map it to the same netlist.
right, right.
So that's how it is. Then this can be nested. This
Okay,
ternary operator can be nested. For example, uh, you have this A, B, C,
yeah,
and D. Here you have this S1, S0.
yeah,
So now you can simply put here assign y equal to your S1, S0. You can concatenate like this. This is called
yeah.
concatenation operator. So
Okay,
using this concatenation operator, you can check this is that three.
okay.
So if that's three question mark, then you are going to assign like this is zero, this is one, this is two, this is three. So D you are
Yeah,
going to assign.
okay. Yeah,
Else you are going to check another condition is S1 comma S0.
yeah,
Is that equal to two question mark?
yeah.
If that's true, then P is assigned.
Okay,
Else now another condition. S1, S0 is compared to the one. If that's one,
yeah,
then question mark. Then B is assigned. Else A. You don't need to check the last one.
yeah, yeah,
So then terminate with a semicolon.
yeah,
So that way this nested this is nested.
yeah.
So nesting of this ternary operator is also possible.
Okay.
For readability purpose here, what we have to do is after this first comparison when you have done question mark, then the
Yeah,
true statement. This is the true statement now.
yeah,
So after the true statement colon,
yeah.
this entire thing is a false statement actually till here.
Yes.
Now, if you take this one here, that is it's not. So now, if you talk about this inside this parenthesis, inside this big parenthesis, this
Mm-hmm.
condition when you are checking here, this is okay, true statement, but
Okay,
this entire false is actually one false. This entire thing is false.
okay. Yeah, yeah.
So like that, for readability purpose, you have to keep this parenthesis.
Right, right. Yeah,
So by carefully keeping those parentheses, you can nest the ternary operator
yeah, yeah,
or conditional operator.
yeah,
So the two names are one is ternary or the
yeah.
conditional.
Yeah, but we will be mostly using that one single line syntax instead of using these two other options, right?
Single line.
The can you go up?
Yeah.
This one. Yeah, this one. This is what we are using mostly, right? This what I have seen mostly people
No,
using.
no, no. People even use this one. Where
Okay,
that depends on the requirement, na?
right.
Here the requirement is only 2 by 1 marks, na? This is.
Yeah, yeah.
But here it is 4 by 1, na?
Okay, yeah. Then it
Then
changes.
then compulsorily you have to nest, na, like this.
Right,
You just cannot do with the two.
right. Yeah,
So that is what the this one. So let's now stop this one. Let's go to the coding part.
yeah.
Uh,
Uh, can you write the code? Then this recording will be like in the same video itself. Then it's easier for me
that
to
part,
refer.
no, no, that part. I will instruct you.
Okay.
So just a minute. Okay. So in design.sv,
Right.
hmm, 1 minute. What's this? Module space mux 2 by 1.
Should I write
I will keep
to
telling you.
like this?
That's okay. Open the parenthesis.
Okay.
Input
Yeah.
space A comma B comma
Yeah.
press enter, press enter. Input yes comma enter. Uh-huh. Output Y. Enter.
Yeah.
Close the parenthesis, terminate with a semicolon.
Yeah.
The reason for you making use of two inputs there, no, no, hold on, what is happening? For saving, you have to select the tools. Go to the tools. No, no, left,
Tools.
left, left, under left tools.
Okay.
Click there.
Tools.
Select. Go to select. Drop down menu. There,
And
alt deck. Uh, Now you can save, but save it with save with a proper name. Their ad title is in the bottom. There mux 2 by 1,
mark, mark
2 by 1
one.
using df. Df means data flow.
Yeah.
Now save. Now save.
Okay. Okay.
So now, I was telling you that the reason for using twice the input keyword is
Yeah.
generally we consider select line as a control signal.
Yeah. Yeah.
Just to distinguish input lines from the control input lines, we are
Yeah.
using AB separate and S separate.
Yeah. Just for the readability.
Yes, just for the readability.
Yeah.
There you press enter, assign space Y. No, no.
Why?
Uh,
Oh, why? Okay.
Equal to yes question mark B colon
Colon.
A
Yeah.
semicolon.
Semicolon. As in this one.
Press enter. End module.
Yes.
Now come to this side, test bench side. Uh,
Yeah.
Here, backcourt. No, no, the
Okay.
backcourt.
Not
something like this?
Yes, yes. Their module
Yes.
space TB underscore MUX 2/1.
Yeah.
MUX 2/1. Next line. Next line. Go to the next line.
Okay.
Their reg.
I have to put this bracket open as this thing,
No
right?
problem. That's fine. You just go to the
Okay.
next line. Reg
Yeah. Yeah.
space A comma B
B.
semicolon.
Yep.
Enter. Reg
Yeah.
yes semicolon wire y
Yeah.
semicolon. And here you have to instantiate your module. So that is MUX 2/1.
Yeah.
2/1 space. Instantiation name is compulsory.
Okay. Yeah.
There you have to give M1. Any name you can give, by the way. Open the parenthesis and keep in that order, same order. A, comma, B, comma, S, comma, Y. Close the parenthesis, terminate with a semicolon. Press enter.
Yeah.
Initial. Press enter. Begin. Press enter. Dollar monitor.
Dollar monitor.
Open the parenthesis. Dollar time, comma, double quotes. A equal to percentage B. B equal to percentage B.
Equal to percentage B.
S equal to percentage B.
Percentage
Y equal to percentage B.
B. Yeah.
Uppercase also okay, fine.
Okay.
That format specifier lowercase and uppercase both are permitted. Comma.
Comma.
No. Double quote. Put the double quote, then comma.
Okay.
Now A, comma, B, comma, S, comma, Y.
Okay.
Close the parenthesis and terminate with a semicolon.
Okay.
In the next line here, what we have to do is we have to give various values for we can fix A and B. It's up to us.
Yeah.
It's up to us how we want to give. But I'm telling you,
Right.
let's keep A and B fixed. A equal to 0 semicolon, B equal to 1.
B equal to 1.
Now let us give S equal to 1 semicolon, hash 5, next line, hash 5, after delay of 5, hash 5 semicolon.
Okay.
After delay of 5, we want to give S equal to 0.
Okay.
Again, hash 5. We want to give S as 1 again.
Yeah.
Now the line number 13 to 19 you copy.
Okay. 19.
13 to 19. 13 from 13 to 19. Copy 13 to 19.
Yeah.
Copy. Go to line number 20.
Yeah.
Paste it. There you
Yes.
change A value as 1, no, A value
Yeah.
as 1, and B value as 0.
Okay. Yeah.
Now, after at line number 28,
28. Yeah.
give hash 5,
Five.
semicolon, dollar stop,
Dollars. Stop.
semicolon. Press enter and end. Press enter, initial, press enter, begin, press enter, dollar, dump file.
This thing, right?
Uh,
Yes.
there you FA, there FA, na, MUX 2 by 1 you type FA. You can keep FA also, no issues with that. That is not going to give any error.
Okay.
Just because we are doing MUX, so I prefer to have their MUX 2 by 1. Okay.
Yeah. Okay.
Okay. So then save it. So now run.
This one was open EV.
In case if you want waveform, you have to select that. Now
Yes,
save
and then
again. Save again.
save again. Right.
Now run.
Then run.
Hmm. Read where what it is saying. Their test bench
Uh,
dot
but
sv line number 33. Some mistake it is complaining. So initial line number 32.
in the I think
Save it. Run now.
yeah.
So now this waveform, the way yesterday we analyzed, you can
Yeah.
analyze, minimize this.
Okay.
Now you can check in the console here. When at simulation time 0, A0, B1, we have select line S1. So whatever the value of B is there, that is appearing on the Y.
Yeah. Yeah. Yeah.
At simulation time 5, S is 0. So whatever the value that is there on the line A, that is appearing.
Yeah.
At
Coming
line
here.
number 15, S is 0. So whatever the value on the A, that is seen on the output Y.
Yeah.
So
Yeah.
that's how simulation is working. It means code is correct.
Right. Yeah. Almost.
So we will stop. You try
Yeah.
that 4 by 1 you try.
Okay.
So the ternary operator usage I had shown you, na?
Right. Right. Yeah. I will
So
look into.
that you can check in case if you have doubt, then you can